Hello everyone, my name is Zhizhou Sha. Today I'm gonna present our WACV 2025 paper, Differential Privacy Mechanisms in Neuroattention Kernel Regression, to you. This paper is done with my co-authors, Jiuxiang Gu from Adobe, Yingyu Liang from the University of Hong Kong, and me from Tsinghua University, and Zhenmei Shi from University of Wisconsin-Madison, and Zhao Song from the University of California, Berkeley. Today, my presentation will go into the following orders. So first, we will introduce the background of differential privacy. Then we will introduce the background of neuroattention kernel regression. Then we will present our main result, DP-NTK regression. And we will also present our experiments where we testing our DP-NTK regression on the CFR10 dataset. Finally, we will briefly conclude our contribution. We will start from introducing the concept of differential privacy. The core idea of the differential privacy is to provide privacy guarantee for the individual's data. So first, let's focus on the figure on the left-hand side. So for example, if we have a database D1 and there is an attacker, the attacker have an analysis named M. So for the database D1, the attacker can use the analysis M to get an answer A. Then we add the JAWS data to this database one, D1. So we will have a database D2. So our goal is to protect the JAWS, the privacy of the JAWS data. So we would not like the attackers to get information about JAWS data. The attacker can use the analysis M on the database D2 to get answer B. So our goal is to make the answer A and the answer B somehow indistinguishable. By this way, we can protect the privacy of JAWS data by not letting the attacker know the difference between the A and B. Then we will introduce some mathematical definitions of differential privacy. So we first introduce the epsilon dp. For epsilon dp is that we will first calculate the probability of observing the output O from the database D1 by using the analysis M. And then we will also get the probability of observing the O from the D2. We define the epsilon dp by the probability of getting O from D1 divided by that from D2 will be less or equal than the exponential epsilon. However, this is a really rigorous DP privacy guarantee. So sometimes we can also afford some failure probability. Delta here denotes the failure probability of getting epsilon dp. An intuitive understanding of epsilon delta dp is that the epsilon dp will be guaranteed with probability 1 minus delta. So then the equation will be changed to that. Then we will move on to introducing the neurotangent kernel regression. The neurotangent kernel is a kind of thing that we use to analysis the process of deep learning models. So we will first start from introducing the discrete version of the NTK kernel. We will have some weights WR drawn from the Gaussian distribution where its mean are zero and the variance are sigma square multiplied identity matrix. This fixed weights can be viewed as learned neurons in the deep learning network. We can use this. We can use the following equation to emulate the learning process of the deep learning neural network in this discrete formula. In the ideal case, there are infinity neurons. The M should be extremely large. We actually substitute the average operation in the discrete version of the new NTK kernel to the expectation here. Here we also define the continuous version of quadratic NTK kernel. Then we will move on to define the NTK regression. For the NTK regression, so we first introduce define the kernel function. The kernel function of the original training data, these two parts combined together, we will get a matrix K. And this K is only calculated from the original training data. And then we can also calculate an alpha with the help of the original training labels. Then we will get an alpha. After that, for each query data X, So if we want to tell this new data X, we will first apply this X with the original kernel function and also the original training data. Then we will also use the alpha to multiply it to tell which classification the new data X should be. One problem is that you can see here when calculating the alpha, there is an inverse operation in this equation. We need to guarantee that the K here to be a PSD matrix. Here the PSD denote positive semi-definite. Only the K is PSD and it add a lambda multiplier identity matrix. This matrix can guarantee have an invertible matrix. This leads to a further problem that the classical differential DP mechanism such as the Gaussian mechanism and Laplace mechanism cannot guarantee the cannot provide privacy guarantee to the K matrix we mentioned in the previous page. This is because that the K matrix need the PSD property after it is added the noise. Here we use another mechanism named Gaussian sampling mechanism to provide the privacy guarantee to the K matrix. The Gaussian sampling mechanism is that if you given a fixed matrix, a PSD matrix, here we denote as the big sigma matrix. Then we will sample many vectors from the Gaussian distribution, where the mean of the distribution is 0 and the variance of this distribution is big sigma. Then we can approximate this sigma hat with these sampled vectors. So in this way, we can guarantee that the sigma hat is also PSD, since the sigma hat is the approximation version of the original sigma matrix. So we can also have the privacy guarantee for the sigma matrix. Then we will move on to introducing our DPNDK algorithm. Our algorithm actually provides a privacy guarantee on two parts. The first part is the matrix K. We use the Gaussian sampling mechanism mentioned in the previous page to add the privacy guarantee for the K matrix, also denoted here in the line 4 of this algorithm. And then we will use the classical Laplace mechanism to add the privacy guarantee to the original training data X, also here in the line 6. Then we can run the composition lemma that we can guarantee our NTK regression is also have the privacy guarantee. The entire algorithm can be shown on the right-hand side here. Yeah. So then we will introduce our experiments. We actually evaluate our DP NTK regression on the CFR10 dataset, where we evaluate with the image classification task. The image classification task is to require the regression model to classify the image to 10 classes. And here is the experiment result of ours. And we can see that when the privacy budget is very low, which means a very high privacy guarantee. For example, log epsilon here is only 1.5, and our method only still keep around like 75% accuracy on the classification task, while the non-private version is only have like 82 or 83 and 83 accuracy. This experiment demonstrates that our method can have a very high utility guarantee along with a very high privacy guarantee, which showcase the power of our algorithm. Finally, we will briefly conclude our contributions. We have present a novel differential privacy mechanism on neural tangent kernel regression, which is the first attempt on making neural tangent kernel regression private. And also, our work have shown that have provided theoretical analysis and empirical validation, showing that our DPNDK regression maintains high privacy guarantees along with high utility guarantees. That is all my presentation today. Thank you for your time and your attention for listening to this presentation.